and record. So welcome everyone to our meeting for Introduction to Networks this week, the week of 419. Had a question, and the question was about lab 379, which is installing Wireshark. This lab does not have an equivalent in NetLabs. In other words, it's not something that we can do in NetLabs. We can do 3710, but not 379. So if you're able to do it locally, in other words, if you're able to actually install it on your local machine in your office, you could try that. You don't have to actually do this because we've got Wireshark installed in NetLabs. But if you get a chance to play with Wireshark, Wireshark is a great program. And in fact, there's even, you may have heard of Wireshark University. I don't know if you are aware of this, but there's actually Laura Chappelle, who has an entire university around how to use Wireshark. You can become Wireshark certified. There's even a Wireshark certification so that you learn how to troubleshoot with Wireshark. Very unusual. I'm getting unstable internet connection. I'm sitting in my office, which is extremely unusual. But this is one way you can get certified in Wireshark. But for us, for this particular lab 379, if you can install it locally, that's fine. You can play with it. You can actually put it on your PC at home and actually do some captures. More than likely, I would not suggest installing this on your PC in your office because your IT department's probably going to get mad at you because it is a sniffer and it is a wire. It's basically a protocol analyzer. So it allows you to grab packets and it turns your PC into what is called promiscuous mode. So you can do it locally and upload it, or if you want to, you can just skip 379. Either one that's good for you there. I do want to talk a little bit about our class again, and that is assignments and a quick review of those assignments. And that is the following. I want you to be aware that, again, we have basically you read each module, and then it's optional. I'm putting out lecture videos for you, and you can either watch those or not. That's your choice. I think they're pretty helpful, but you may think that they're terrible, so it's your choice. But I'm putting out lectures for every single one of the modules that we're going over in the Introduction to Networks. And I'll be doing the same for our our future class, CCNA 2. We then have your packet tracers, which you are completing with your packet tracer, and then labs. And remember, there are two types of labs. There are the written, exploratory, non-equipment labs. And then there are the labs that do require equipment. So as we look in these labs here, looking at our setups, this was the first lab you did, which was just a research lab. And then there are other labs that are the same way, researching networking standards. This one is a little different because technically you could install it on your local machine if you want to. But I want you to be very clear on one thing. When you go to do labs with equipment, they are the labs in your syllabus that are in bold. And when you go to do one like 3710, there's in the real world, you could do it on your local gear at your school if you had local gear. For our class, I'm obviously having you use NetLabs. But be aware, in NetLabs, when you go to do this lab, you must use the lab document from inside the content tab. I had someone today have a problem with the lab, it wouldn't work, and they were using the document from inside the course. But if you use this document right here, you'll notice it is not modified to work inside of NetLabs, so it's not going to work. This one is modified to work inside of NetLabs, and it says so. Now, they were still having a problem with the IP config/all. Really, you're not supposed to get an IP address. They're just trying to show you that you will get actually should get an IP address of 192.168.1 dot something. But this lab's very different than the one that is inside of the curriculum. So anytime you do a lab on NetLabs, make sure when you do this, okay, I'm gonna go schedule it. So obviously I'm gonna click here, I'm putting that straight to voicemail. And you notice how there's all these reservations here. But just go out here and there's more pods available. We have 16 pods right now. We will soon have 20, hopefully, depending on how the chip shortage continues to work on our access to devices. But as this lab is booting up, once it boots up, I'll show you where to get the content. Again, it's on the content tab. So when we get in here and the pod is initializing, when you're doing a lab in NetLabs, do not use the document in the curriculum. Use the document that is inside the NetLabs reservation on the content tab. So right here. If the lab you're doing the lab in with NetLabs doesn't say this lab has been updated for NetLab Plus, it probably will not work on our NetLab system. Does that make sense? And Anthony, I got your email about the other issue. I'll look into that. Okay, I know there's been an issue with the getting an IP address via DHCP. So I'll do that. But most of this lab is just opening up and looking at the PCAP capture that takes place. So questions about that? All right, so I just want to once again go over how the assignments work. So NetLab system, you must use the lab documents from the content tab. And the bold labs in your syllabus are the ones that are on netlabs.stanley.edu. I keep forgetting to put my S on there. netlabs.stanley.edu. All right. Any questions on that? All right, so I did that one. There's your logins. Everyone knows that, netlabs.stanley.edu. Your username is your SCC email address. The full address, your initial password is Cisco123. Someone have a question?
Kelly, the NetLabs is part of the Net Academy, or is it different?
No, it is a completely different system that is by a third-party vendor, and we purchase it ourselves, and we have an entire data center that we are running it on.
Okay.
So I'll give you a good example.
Yeah. Okay, you mentioned that last time.
Yeah, and let me show you. I did actually take 2 pictures of my data center today. So let me actually show you. When you actually connect to and do a lab on our NetLabs, you're using this system right here. This is our data center. Pull it over here. This is our data center that I manage. You'll notice a Vertiv data center, and inside of that data center is where we have our gear. And here is an example of that gear as it sits inside of the rack. So it's kind of neat. Whenever you do a real lab, you actually connect to one of these pods. There's pod 1 right there. So when that pod boots up, these devices boot and you have access to this real Cisco gear. We have 2 full racks of gear right now, and we're actually working on our 3rd rack. And that doesn't count the gear that's in our actual classroom. But that's what you're connecting to, which is really neat because it's real equipment. It is not a simulated environment. But that is completely separate from NetAcad. For you, you'll probably have real gear sitting in your classrooms, and that's what you will use for your students. All right. Questions? All right. Well, I want to talk about models, folks. I want to talk about different types of models and how we can use those models. So for instance, we talk about 2 main types of models, and those are the open system interconnection model, which is a reference model. And the reason we call it a reference model is because we don't have in the real world an OSI model or an OSI protocol stack. Now, I will tell you, it does exist. All right, there is actually the OSI protocol stack exists. It is a protocol stack that nobody uses anymore. Okay, we used to, but we just don't use it anymore. The real world model that we work in is the Tcpip model. Now I'm going to pull up my whiteboard here, and I've actually started using, I got me a little Intuit or Wacom tablet, and wanted to go over the model again. So when we look at these, we've got on the left side, we've got the OSI model. And the OSI model consists of the 7 layers of application, presentation, session, transport, network, data link, and physical. Now, folks, my handwriting is horrible, all right? And I apologize, but I got 2 excuses. 1, I'm left-handed. And 2, I have been hit by a truck, so I can barely use my hands as it is. So when I'm actually using this tablet, and when you watch the videos that I do, just cut me some slack on the fact that my handwriting is so bad, because it is atrocious. Plus, using this tablet is a little bit tough. But as we've talked about in our discussions, the OSI model, these layers here map to what occurs at the application layer of the TCPIP model. Transport maps 1-to-1. The internet maps to the network layer. And then the data link and physical layers are mapped to the network access layer in TCPIP model. Now, this is a real world model because we run TCPIP on our devices. I used an example inside of my lecture, and this is one I used to put models together all the time. Put a lot of, I actually still put little models together, but I really enjoyed putting models such as F-16s together. I went through a kick where I put tons of F-16s together. Yes, I will. Is that better? Did I help, Glenda? Just let me know. But even the best model, if you go get a Hasegawa and you pay several $100s for, I don't know what is going on with my internet connection here, folks. I'm in the office, which is usually the best place for me to be, but I've gotten 2 different things saying that the internet is unstable. I don't really know. I could drop out and come back. Let me finish this real quick. This model, even though it's one of the best out there, may only have a couple hundred pieces. However, the real F-16 has a couple million pieces. So that's why the reference model, which is the OSI model, didn't survive contact with the real world. So TCPIP is the model that we actually use in the real world. Is it still bad, everybody? Is it getting better? Or has it gotten any better? And now I've got a phone call again. Ignore it. Any better? Just let me know. Like I said, I know it's very, very unusual for us to have problems with connections.
It's still a little choppy.
Still choppy.
In and out my end, Kelly.
All right, I don't really know what to do, folks. Like I said, it's extremely unusual to be choppy with our internet here at work. Don't think I'm downloading anything. Don't know. But let's go. I'll continue. If it's still choppy, maybe the recording won't be choppy.
Cotto.
Do what, Francisco?
Okay. Professor Cotto.
Yes.
You sent the link for YouTube for this session, and there you have this these charts that are printed. I don't know whether you can get it from there. Just go to that section.
I can, but then I mean, I can get it out of the curriculum. There's no problem. I mean, I can go to the curriculum and grab it. How about the rep here? I mean, I can show them here. I was just trying to actually, there it is. That's how they map. Let me try something, folks. Okay, how about now? Did that change anything? Does that help at all? Let me, actually, folks, we're gonna run a, okay, it did not help. All right. Well, here's what we're gonna do. We're gonna actually do a capture. We're going to use that one.
Yes,
Yeah.
I can see your screen. Yeah.
Can you see my screen now? So I am trying to see what all is causing issues with, so it's all UDP. Okay. Let me pull back over here. All right,
Yeah.
I'm gonna pause the recording. Okay, so you can see my screen. So let's try from here. We'll see what we can get done. So that real world model, the OSI model versus the Tcpip model, it is very important that you understand the difference between these two models. It is very important that you learn the different layers. All people seem to need data processing, or please do not throw sausage pizza away. Those are the two different mnemonics you can use to remember them.
I can't see your screen.
Oh, okay,
We can't see your screen. We can't see your screen now.
okay. Now you should be able to. How about now?
Yes, we can see your screen now.
Good, good. Okay, so again, 7 layers. All people seem to need data processing. Please do not throw sausage pizza away. These are the 2 ways that you can remember. It's a mnemonic to help you remember it, or also the Tcpip model ITN, Application Transport Internet Network, or NITA, NITA. Did anybody watch the video I had on module 3 and remember why it was so important that the Tcpip model has no protocols listed at layer 1? What was that reason? What made it so good?
So you can connect to any different, I think, different type of devices.
Exactly. It was the
Protocol.
beauty. Go ahead. Go ahead.
I was finished. I was just saying it was related to the protocol types, different protocols.
Yep, the different layer 2 protocols and layer 1 protocols that could be used. So they were smart enough back in the late 60s, early 70s to say, we don't know, they had no clue fiber optic cabling was coming. But by not defining Tcpip to only run across copper cable, it was able to be modified to run over fiber optic cable and over wireless. All of that was available because they were brilliant enough not to make a set standard. We, in our daily world today, Tcpip is the model we use the most. It is the one that we have running on all of our systems for the most part. As we look at the physical layer, that's one of the things I want to talk about also. As we look at the OSI model, and we look at the physical layer are our layer 1 components. So it is anything that is a cable, a connector. There are also devices called repeaters. Sometimes you will see, good. I think it may have been, believe it or not, I think it was actually the little Wacom board. I think something on that, the driver was causing an issue, which is extremely aggravating. So I have to figure out what that is and reboot my system. But I really think that's what it was. I disconnected that Wacom tablet and everything seems to be working better now. So go figure. It's the only thing, by the way, there's you a lesson in troubleshooting. The only thing that had changed on my machine was I had plugged in this Wacom tablet. So to fix it, I unplugged the Wacom tablet and hope it works, which it did. So the physical layer, we talk about it in the lecture I've already sent out to you, but in the physical layer, we talk about copper cabling. We talk about the need for encoding And the fact that encoding is how we get things to be ones and zeros on our particular cabling or media. And depending upon whether it's an electrical signal, it could be an absence or presence of electrical current. It could be a change in electrical current from high to low or low to high. It all depends on what type of encoding you're using. But all of that is used to allow you to be able to send across the physical medium ones and zeros. In this case, here's an example of copper cabling, which copper cabling is one of our most used types of cabling. It is extremely easy to use, easy to work with, cheap. They don't do it as much now in the curriculum, but we used to actually make cables as part of the curriculum. I wish we still did, honestly. We would make unshielded twisted pair patch cables, straight through cables, and also rollover cables. But it's not, they don't have labs on it anymore. By the way, Anthony made a good point. Anthony had a problem with a Mac, and I believe the drag and drop that was in this particular section. And there is a way to fix it. So if you got a Mac and you're having problems with drag and drop, the other thing I've found out is on these like this, if you've got a touch screen, it doesn't like to work on a touch screen for some reason. But if I move it over to a non-touch screen, it actually will usually work. But it does not like to work on a touch screen. So just be aware of that. But these are the pinouts for 568A versus 568B. And all they do is, as I mentioned in the video, the lecture, is reverse the orange and green pairs. So 568A is actually white, green, green, white, orange, blue, green, orange, white, brown, brown. 568B simply reverses the oranges and the greens. So pretty easy there. Now, fiber optic cable is one of our best types of cabling. If you need to resist EMI, you need to travel long distances, you need to ensure that you've got really future-proofing your network, because we don't really know how much can be carried on fiber at this point, other than the fact that we've got our end devices on each side that can push the amount of information going across a piece of fiber. We will continue to see the ability for fiber to move more and more data as we go forward. Questions about the physical layer. I call it the blue collar worker of the networking world because I call it a bit pusher. It literally just moves ones and zeros across the network. Any questions on this? Again, I recommend going over my video and watching it, because I talk about the difference between what I call simple twist versus simple click connectors. If you ever worked with these, you know that these you have to push on and twist, whereas these, they click. And now my internet is unstable again, so it is not the Wacom tablet. Looks like I just broke up again, so it must be something here on our campus. All right. Questions about layer one. What's the difference between multi-mode and single mode fiber? Anybody? There are two primary differences.
Single mode travels at a longer distance.
Definitely. And it uses a single light going through the core. What usually powers single mode? What do we?
Light?
It's light, but typically it's a laser. Single mode typically uses an actual laser to produce the light, which makes it much more powerful, which can make runs of tens of thousands of kilometers. Multi-mode puts multiple light paths in on the core, and it usually uses LEDs. So it uses a smaller LED. Can't travel as far, but it's a little cheaper and a little less expensive. So a lot of times across our campus networks, we may be using multi-mode instead of single mode. And then for anything that is what I call long haul, we use single mode. Questions about wireless. We got a whole section on wireless later, but I always tell people, everybody loves wireless, but I 100% believe if you can put a cable on it, put a cable on it. You think about it, you know, wireless has security issues. It has bandwidth issues. It has interference issues. It's a wonderful thing, but if I can put a cable, I'm going to run a cable. I actually have, again, in my house, 1,500 feet of coaxial cable, RG6, and about 3,500 feet of Cat5e cable that were put in the walls when I built my house. I did it myself. I actually run all the cabling. Any questions on the physical layer of the OSI model? One thing I do want to go back real quick and mention is this, and this is a very important concept for you. And that is that one of the benefits of a layered model is that each layer is independent of the other. In other words, if you look at these models, each layer does provide services to the layer above it and receives services from the layer below it. But the data link layer really doesn't know what is going on at the network or the transport layer. The example I gave in my video is I compared to like the Russian dolls. So when we're encapsulating information and it's getting placed into these Russian dolls, well, you really don't know what's inside the doll above it or below it. And so the transport layer can do error checking and the data link layer can do error checking. And people get confused and say, well, I thought the transport layer did error checking. It does, but it does transport layer error checking. The data link layer does frame check sequences, as we'll learn here in a minute as we look at the data link layer. The good news about this and the fact that it is modular and that the layers, while receiving services from below and providing services above, when a new protocol comes out, like IPv6, instead of having to completely rewrite the TCPIP model, you can write IPv6 to work as an internet layer protocol, receive services from network access protocols below it, and provide services to the transport protocols above it. And so it can be easily replaced. If a new version, if IPv9 comes out or v10, as long as it's able to be written to where it can talk to the transport layer and receive services from the network access layer, it will be able to be dropped right in here without having to rewrite the entire model. That is the beauty of a modular system, a modular model. Questions about that? Because what I want to do next, I'm going to skip the number system. You can watch that video. It's just how to convert binary to decimal, decimal to binary, and hexadecimal. But I want to talk about this, the data link layer. So we're moving up above the physical layer. We're going to talk about the purpose of the data link layer, looking at some topologies and the data link frame. We talked about PDUs and what the data link does, but now the data link layer is responsible for framing, for placing the data into the correct format to be placed on the wire. In other words, there's a frame type that corresponds to different data link protocols. Can somebody name for me a data link protocol? Anybody? Anybody want to come off mute and name for me a data link protocol? Don't know where my notepad is. There it is. Well, folks, one data link protocol is Ethernet. Okay. PPP, it's data link layer. HDLC, high level data link control. These are all data link layers. So if you're running Ethernet, you must eventually take the frame and frame it to be an Ethernet frame or a PPP frame or an HDLC frame. So the data link layer is responsible for that framing. You're also going to find out that it's responsible for error checking, but it's going to be responsible for error checking at layer 2 using frame check sequences. And that's going to be part of the actual frame itself. So as we look here, we will see that at layer 2, or at the data link layer, every device has a layer 2 address. Okay. Now that address is going to be completely dependent upon your layer 2 protocol, because you'll find out that actually HDLC, which is designed to do point-to-point, and also PPP, because they're point-to-point, you don't really need data link addresses. But with Ethernet, we're going to have a special one called, in fact, it's called a media access control address, or you've seen it called a MAC address. That MAC address is going to be a layer 2 address burned into the NIC itself. So the layer 2 header will have the destination NIC, which is the destination MAC address, and then the source MAC address. And then you'll see there's also a layer 3 header, but that's added, and really layer 2 is not even, doesn't have a clue what's in this layer 3 header. It just puts its information at the beginning. 802, which is anything that uses Ethernet, has 2 sublayers. I talked about logical link control sublayer and the media access control sublayer. And you'll see the different, here's 802.3, which is Ethernet, 802.11, which is wireless Ethernet, and 802.15, which is standards for wireless personal area networks like Bluetooth, RFID. But each one of those has a MAC sublayer that's written for it so that you can run it. And then what's important is you've got to have a way to get up here and talk to the network layer, whatever you're running up here. We're running most of the time IPv4 and IPv6, but you could be running IPX-SPX in an old network. You could be running other protocols like AppleTalk. That's an old network layer protocol. But to do that and still run on Ethernet, you have to have this logical link control sublayer, which you'll notice that down here in the MAC sublayer, we're really talking about physical addresses. We're talking about the addresses burned into the NIC or associated with the device. Up here at the network layer, we're talking about logical addresses, which are completely logical, have nothing to do with the physical the device itself. So this LLC sublayer acts as a go-between between the physical components and the software components. And that's why you can have multiple layer 3 protocols on the same interface and media, because the LLC sublayer can control that between the lower levels and the upper level protocols. So the MAC sublayer does frame delimiting, which we'll see how the frame does a startup frame delimiter, how the frame is set up, addressing, so MAC addresses, and error detection, which we'll see in a few minutes, is going to be a frame check sequence that's placed at the end of a frame. In fact, let me jump ahead real quick and just show you the frame, because I think it's better to show it right now. So when we look at the frame fields in layer 2, here's what we normally have. A frame start, which is typically some series of bits, a series of 1s and 0s. You have the addressing, which has the destination MAC address and the source MAC address. The type, which tells it what layer 3 protocol to pass it up to. Different types of control, such as quality of service, differentiated control service points, DCSPs. The data, which this is the layer 3 and above information that's going to be passed up. And then we've got the frame check sequence, or the error detection, which is attached. So what happens with every frame that leaves a device running Ethernet? It runs a mathematical calculation and does a frame check sequence and attaches that to the frame. And the frame is received on the other end. That receiving device runs the same calculation on the frame. If the two numbers match, it assumes the frame was not damaged in transit and will accept that frame. If the frame check sequences do not match, that frame is discarded and will have to be retransmitted because it has been changed in transit. So that's how we can have layer 2 error checking. And we'll find out later that you can do error checking at layer 4 also. Okay, so that's error detection. So that is the frame itself. I'm gonna jump back up here. So as we're doing framing, we do it based upon our MAC sublayer. Questions about that? So if you are a receiving machine, you would accept a frame from the medium, you de-encapsulate the frame, and then if you need to reply to that, you would re-encapsulate the packet into a new frame and then forward it to the next medium. So the data link layer is responsible for that process. We'll learn too that routers, actually every time a frame passes through a router, the frame headers are rewritten, which is important to note. So our standards, same organizations we had before, are responsible for these standards. We also, when we talk about layer 2, we talk about our topologies. We talk about different physical and logical topologies. So physical topology is the way the actual devices are connected together, whereas your logical topology is how data moves in your network, which could be very different than the logical or the physical topology, depending upon how you've subnetted things, depending upon how your network has been devised. WAN topologies versus LAN topologies. WAN topologies consist usually of a point-to-point, which is one device to another device, hub and spoke, so a central hub going out to different spokes. And then I like to pick about this being the satanic one, but mesh, where all devices are connected to all other devices. Your type of WAN topology will be completely dependent upon your needs. If it's point to point, the problem here is you only have one exit and one entrance on your network. Hub and spoke, you may have multiple connections depending on your network. And mesh obviously is the most resilient because you have, if you lose a single link, you still have full connectivity. The reason we don't do mesh on everything is it increases complexity and it definitely increases cost. Because imagine if every one of these is a piece of fiber that you're having to lease. If it is, then your costs go up exponentially. So here's a point-to-point between two nodes. Here's a point-to-point, but inside you've actually got a cloud that's actually hidden from the source and destination nodes. This can be because of things like MPLS clouds, or possibly it could be because you've got a some type of VPN set up so that the source node and destination node thinks they're directly connected, although they're not. Our LAN topologies used to be bus, and that was just like this. A bus topology, you had these T connectors that you connected, and on each end you would actually put in a, on the ends you would put in, oh golly, I'm losing the, oh, somebody help me out. Oh my goodness, they stopped the signal. Basically terminators, we put a terminator on each end so that the signal couldn't bounce. But this is the old full bus topology. Almost nobody runs a bus anymore. Most of us are some type of star, which has a switch at the center, or an extended star that has multiple switches, and those switches are connected by what we call home run connections, or interconnects between different switches. We don't use rings in the LAN anymore. We still do have those topologies for possibly some of our WAN connections, but in the LAN, we used to have a thing called token ring. And token ring literally had a ring, but most of the time it was a physical star, a logical ring. That's one of the examples if you do much reading on token ring. By the way, token ring is quite honestly a better method of accessing because it used token passing, which is a deterministic type of access method. However, because it was controlled by IBM and they did not allow anybody to make generic components, it became too expensive compared to Ethernet. So even though Ethernet was not the best technology, it won because it was able to be cheaper and good enough. Now, we do need to think about these two methods here, which are called half and full duplex. Half duplex, this is how I describe it. I love watching Discovery Channel, and I've always dreamed of climbing Mount Everest. Unfortunately, after my accident, that will never happen. But I always like it when you sit there and says base camp to camp 2 over. Why would they always say over? By the way, I'm not very good in my British accent, but why would they say over? What is it about walkie-talkie that makes it half duplex? Anybody?
Only one person.
One person
One way.
talking at a time.
At one time.
Exactly.
Having only one way.
Only one way, Jacob. Exactly. And Jelani, exactly. I think I said your name again. Wrong, Jelani. But only one way communication. It is literally, I can either send or receive. I can't do both. So with half duplex, if we're in a situation with half duplex in our networks, collisions can occur because you can only send or receive. That's why they go over, because that's telling the other side they can then send. Now, we have gotten away from half duplex in almost everything we do now. We now have full duplex where we have a send channel and a receive channel. So you can send and receive. By the way, that's one of the things in the physical layer. If we were to go back and look at 568A and B, you have a pair of wires for send and a pair for receive, so that you don't have collisions. In a modern network, we should never have collisions. If it's meeting all the standards for the physical layer components, and if it's set up correctly, you should never have a collision in a modern network. Now, we still need to control how you get access to the media. Now, the two main ways are contention-based and controlled access, or contentionless. So contention-based is you're going to fight for access to the media. Even though, and this really again is legacy, because really we should have no chance of a collision, but the way that Ethernet works is it will carrier sense. Each device listens to the media and says, is it open? Can I send right now? Because is there any data on the line? If there's nothing on the line, then it can send. Now, that means that's the multiple access part. So technically, in this particular instance here, if there was an Ethernet hub, by the way, a hub would mean you're doing half duplex, it would be possible for two PCs to look at the wire, find it to be empty at the same time, and send at the same time. If that happened, a collision could occur. And if that happens, then you've got what's called collision detection. So the first machine to see a runt, which is a frame below 64K, which is typically the outcome of a collision, would send a jam packet, and all machines on that segment will then wait a random amount of time before they resend. It's key they wait a random amount of time, because if they waited 10 seconds, then they would just continually have collisions. So it's a random amount of time based upon a thing called the backoff algorithm. So on our legacy bus topology Ethernet LANs, and even though we're in full duplex LANs, they still do this. They'll listen. If it's available, they'll send. If they see a collision, they'll perform the backoff algorithm and resend at a random interval. For wireless LANs, they do what's called Csmaca, collision avoidance. They listen to see if the particular media is available, or medium is available. They then send their intention to send. That's the collision avoidance mechanism. So they actually say, hey, I'm going to send something. And then the access point will say, nobody else can send until this particular device sends. That's why Csmaca and wireless LANs in general are slower than their wired counterparts, because they're actually having to use a slower access method. Both of these are contention based, however, and the problem was that you could have collisions versus controlled access or contentionless, like token ring. Token ring is like Lord of the Flies, where you had the conch, and without the conch you couldn't talk. So in this particular setup with the token ring network, if you've got the token, you're able to send information. If you don't have the token, you cannot send information. The good news about that was you can never have a collision because no one would talk if they didn't have the token. The bad news was it was not being proprietary system that, when I was working with it, a token ring NIC cost over $300 and an Ethernet NIC was $150. And so it just made no sense. Even though it was a better technology, it, basically what they did with Ethernet is they just kept making it faster. Token ring was 16 megabits per second. Then you had 10 megabit Ethernet. Well, guess what? They went to 100 megabit Ethernet, then gigabit Ethernet, and token ring was, by that point, especially once we solved the problem of collisions by doing full duplex, once we solved that problem, at that point, token ring was dead. It had no way to work. So our contention-based PC sends out a frame, hub receives the frame, and sends it out. Okay. Now the beauty of this, again, contention-based is, even though there could be collisions, as we just increase the speed, we could, even with retransmissions due to collisions, you could end up with a faster network than some of the older ones. Now, what we actually have with our non-legacy is we don't have to worry about collisions because the switch ensures through its buffers that there will be no collisions, or there should not be any collisions, as long as you've designed your network correctly. Here is, again, contention-based. I see in the wireless frame that channel is unavailable for a specific amount. So in other words, it says, I see that channel is going to be unavailable for a specific amount of time, so I cannot send. I'm receiving this wireless frame. So basically it comes down to the device says, I'm going to send, signals its intent to send. The access point tells everybody, hey, you can't send anything right now. And then as soon as that frame is received or sent, then it'll open the channel back up. And that's why CSMA-CA it's slower. So it tries to avoid collisions by setting that collision avoidance mechanism up. Questions about CSMA and CSMA-CD and CSMA-CA? No questions at all? We'll talk more about how switches are layer 2 devices, whereas hubs, we know, are layer 1 devices. But we'll talk about how switches handle frames and have a MAC address table of frames. So even though I showed you this, here is that frame field. So we have a frame start, which is a sequence of bits depending upon what type of 802 standard you're using, or MAC layer standard you're using. Your addressing type control. Now, I just had, let me go back over here. I'll start up Wireshark. I'm going to capture, pick my right network. Stop it. I'm going to pull over this Wireshark capture, and we're just going to look at right here, these two devices. So if I dig down into this particular communication here, you'll see that in the frame, all right, you'll see that right down here, it's an Ethernet 2 frame, and the source MAC address is Del 37. By the way, the reason it says Del is because it's D89E. So in other words, it's saying that this D89EF3, we're going to learn, and you will learn, that a MAC address consists of 24 bits that are the organizational unique identifier and 24 bits that are the serial number. But this can be mapped to Dell. So this is a Dell machine. And then this is a Cisco Meraki device that is sending out TCP frames. Okay. And that's because 00180A is a Meraki. We have Meraki switches, by the way. But this shows you the source MAC address and the destination MAC address right here. So we can dig down into it and you can see it. And so each frame has that information in it. I'll go back over here. you can see that the address had the destination MAC and the source MAC. If I go back into Wireshark, you should also see the type flag. So I can find my type here. Frame length 105, frame mark. Let's see, type Ethernet right there. Encapsulation type 1, and you can dig down in it and you actually should see color rule. That's TCP flag. I don't think I have anything. This is just TCP fin and FINAC, so it's actually ending the communication. Let me see if I can find a one that's an Ethernet. Yep. Still Ethernet here. Type IPv4. So right there you can see the type. Let's see if that shows up down here. It does not, because that was a fin. But down here you can see the type field is 0 by 0800. And that is the type that has been placed into this type area. So when you do a capture, you actually see the source and destination MAC addresses. In the frame itself for Ethernet, the destination MAC is always first. You'll learn that is because as it pulls a frame in, when we look at this Ethernet switching module next week, or as I do your lecture for you, you'll see the reason they put the destination MAC first is because devices pull in frames, look at them, and they look at that destination MAC. If it doesn't match their MAC, they throw it away. Now, here's a good example of how MAC addresses are rewritten or actually layer 2 headers are rewritten every time it goes through a router. So if I was communicating from 192.168.1.110 to this web server, we talked a little bit earlier about how the router would have to proxy its MAC address in on an ARP request. So source destination MAC, destination source. We move forward, it gets rewritten to be the MAC addresses of the routers as it moves forward. And then at the final receiving side, it gets rewritten again. So at every hop along the way, the router is completely de-encapsulating at layer up to layer 2, checking to see where the destination IP address is by looking at its routing table, and then putting a new layer 2 header on it and sending it out. When it gets to R2, R2 does the same thing. It'll take it completely apart, look at it, we get it up to layer 3, route it, put it back together at layer 2. So it's really kind of amazing how fast these things take place on our modern networks today. Okay, so I have questions in chat. Okay, no problem. That's no problem. We're almost done. We're about finished with today. Some other LAN, WAN frames that you can look at. Again, I talked about point-to-point, HDLC, high-level data link control, frame relay, ATM, X25. These are older methods, although frame relay is still around, but ATM and X25 are not really around much anymore. Data link protocols at the LAN side. So these are WAN data link protocols. On the LAN side, we have Ethernet 802.11. We do use point-to-point and HDLC on some LANs, and we do use frame relay on some older, much older LANs. Questions about the data link layer. Remember, framing, that's its major thing. Framing and access control, access to the media is what the data link layer does for us. Any questions? Come off mute if you have a question, or put it in chat. Questions about, how many of you already knew a great deal about the OSI model? If you did, just raise your hand or just put in chat, yeah, I knew. I'm very, very familiar with the OSI model. Many of you familiar with it? Okay, Brian's familiar with it. Brian Webb's familiar. Okay. Anybody else? The OSI model is very important because it gives us a framework to be able to talk about both TCP/IP model and the OSI model. It gives us a framework to be able to discuss networking between two devices and how that takes place. Okay, well, everyone, I will get you a lecture out on module 6, although we've technically done it. And I'll also get you a lecture out on module 7. And this is where we're actually getting into looking at an actual Ethernet frame and getting a little more detailed into what Ethernet does. But you'll see it's the same thing. It's got a preamble, which is 8 bytes, has destination MAC address, which is first, 6 bytes. By the way, what's 8 times 6? 48. It's a 48-bit address. The type length, which we saw 0 by 0800 is IPv4. Our data, which is 46 to 1500 bytes, unless we're running jumbo frames, which in the real world, you may learn about a thing called jumbo frames. And then 4 bytes for the frame check sequence, which means our typical Ethernet frame cannot be any smaller than 64 or any bigger than 1518 bytes. But there are ways with what we call jumbo frames to make them bigger, especially inside of our data centers. We'll talk more about that next week and also in the lecture that I'll be putting out later in the week. Any questions?
Do we learn how to turn on the header checksum?
We do not, because that is done automatically by each device.
Okay.
Unless you're talking about, there are ways to turn on header checksums on devices. When you do that, though, it adds a lot of overhead. And typically, you probably only want to do that if you were having issues and you were doing checking. We typically just let layer 2 use frame check sequence, which is automatically on by default. I think that answers your question. If not, we can talk about it more.
Yeah, you answered my question. Thank you.
Okay, no problem. All right. Well, let me stop my recording, everybody.